Cool. Okay. Section 11.4. The comparison test. So yesterday, there was a comment about what happens if instead of just having n to the p in the denominator, I have like some sort of polynomial. What do I do? What can I do something with that? Can I say use that the p series to say something about that? And you can't directly, but we can by using what's called the comparison test. Okay, so let me kind of create an example for us to kind of get us started. So let's say that I'm working with the sum, and I would just start at 0, from n equals 0 to, well, actually, n equals 1 to infinity of 1 over n squared plus 1. Okay, so I have the sum, and I want to determine if this thing is going to converge or diverge. Okay, if you think this one kind of looks similar to maybe some of like the telescoping ones, you try to split this up, it's not going to work because they can't really factor the bottom, which is what's going to happen often in these cases. Or it's not going to factor in something very deep. So I have to kind of go about something different here to see if this can converge at all or not. Okay, and the way I do that, right, is I say, okay, well, this looks very similar to 1 over n squared, except for the fact that there's a plus 1 down here, right? That's the only difference. Okay, let's think about what that plus 1 does, though, right? If I have n squared, and then I add 1 to it, does that make the number, just think about n squared. If I add 1 to it, does it make it bigger or smaller? So if I just have n squared, right, and I add 1 to it, that makes it bigger, right? So then the fraction is going to be bigger or smaller in that case? Smaller. So every term in this series is smaller than their corresponding ones here, right? 1 over 1 squared plus 1 is less than 1 over 1. 1 over 2 squared plus 1 is less than 1 over 2 squared, right? Because n squared plus 1 is always bigger than n squared. So I can say for a fact that this series is less than or equal to. I mean, it really is less than, but I'll just put the equal to because it's not a big deal. It's less than or equal to 1 over n squared. Okay, so if this is convergent, right? If it has a value it pops out, then that number is going to be less than or equal to whatever this number is, right? If it converges. Now, does this one converge? This one converge? Do we know this one converges? Yes, we do. You can use the p series. I mean, we talked about what the sum is yesterday. This one converges, right? And in order for something to converge, it has to be small enough. Well, if this sum is smaller than a sum we already know is small enough, what does that tell me about this one? It has to converge as well. So that is the essence of the comparison test. Okay? So let me break it down. Let me pull out a color and we'll kind of write this out here. So if I have a sum that goes from n equals 1 equals 0, it doesn't matter. I just write 1's the most general, of course, but if I have a sum that goes to a of n, okay, and this is less than or equal to the sum, right? You can compare each term. Maybe well, actually, I'll add that on. Let me see the book. Because okay, no, that's fine. We can do this. So the sum from n equals 1 to infinity, an, is less than or equal to the sum from n equals 1 to infinity of another sum, which we'll call bn in this case. And this is for all n. So no matter what n is, it's always smaller, right? You don't want it to, this one to start getting bigger at some point, right? You want it to always be smaller. No, maybe I'll leave that. And the sum from n equals 1 to infinity of b of n is convergent. Then the sum from n equals 1 to infinity of a of n is, and I'll use my same color scheme here, convergent. Okay, so if I have a series that's smaller than the convergent series, then that one also has to be convergent. Does that make sense? Okay. We also have that if the sum from n equals 1 to infinity of a of n is greater than or equal to the sum from n equals 1 to infinity of b of n, and this is again all for all n, so we want all the terms to be greater. And the sum from n equals 1 to b of n is divergent, then the sum from n equals 1 to infinity of a of n is divergent. Okay, so let's think about this one. Okay, so I'm comparing, I have two series that I'm comparing, right? And I start with the one I'm given, and then I know one that it's close to, that's divergent. And the one that I'm given is always bigger, right? All the terms are bigger than this one. So if all the terms are bigger than the terms in here, and this one's already divergent, that means this one also has to be divergent, okay? So it's basically saying, well, this one's too big. This one's bigger than the one that's too big. So it's also too big, right? You can't say, oh, this one's bigger, so now it's too small. That doesn't make sense, right? That it only has to grow in size. Okay. So those are our basic, those are kind of the rules here, okay? We'll, kind of do a case by case sort of thing, see different examples, but that is the setup, okay? So, any questions for me? Yes.
Like what fonts do you use? Do you just want all of them?
It's just if there's like an easy series that you can compare it to, right? Then yes, you can. There's gonna be some more complicated problems though where you don't really have a good pick for what an easy one is to compare, and so then there's other methods. But yes, this one's pretty powerful in the case that it does work a lot. Okay, so let's go ahead and start going through some examples here, and we'll kind of work through this. Okay, so I'll just kind of run through those problems. Any other questions for me before we start here? Yes. Or where are you saying? Oh, are you saying try to use this for these, or yeah. It goes along with these ones. I wouldn't necessarily. You can't really. Yeah, you can't. Obviously, like if I'm just given a P series, I don't want to use comparison because I can't really. I don't need to compare it, right? And if it's a geometric, I don't really need to compare anything because it's already geometric, so I just use it there, right? Now, I would advise you a lot of times that you could probably get doing integral tests by doing comparison instead. So this one's kind of what I would consider a last resort in most cases. It's there, the option's there, it's available. So it just kind of goes along. I would say that I would say this one's probably one of the first you go to. After you see if you have one of these. right? This one's always first, you always do test for divergence first. And then if it's not one of the two basic cases, then you can kind of hop over to comparison. And is what or we'll get to them with five. Okay, and anything else for me? Okay, let's do some more examples. So we're gonna have a sum from n equals, okay, this one starts with 2, which isn't a big deal. We have 1 over the square root of n minus 1. Okay, so is there a sum that I can compare this to? Potentially. What is it? Hmm? Okay, now, what do we know about 1 over root n? Not conversion, actually. P series says if it's less than or equal to 1, its diverges at square root is less than 1. So this one's divergent. So if we want to make our work here as simple as possible, right? My goal would be to make sure to know this is always going to be greater than this one is, right? So let's think about it. I want to say that this one's greater than this one at all times, right? If I subtract 1 from the square root of it, is that going to make, so let's just compare those two. So if I have square root of n versus square root of n minus 1, which of these two things is bigger? Square root of n, right? Because if I have the square root of n, and then I subtract 1 from it, right? That this is going to be smaller, right? So this guy's the bigger one, right? So what we have is that on the bottom here, right? The square root of n is bigger than the square root of n minus 1, right? So the denominator here is smaller. So does that make the terms here bigger or smaller than the terms here? Smaller, right? So that minus 1 is really important. So because of that minus 1, the fractions here are bigger than the fractions here. Okay, so is it true that this one's greater than or equal to? Right? If all the terms here are greater than the terms here, yeah, absolutely. So is this one convergent or divergent? Divergent. Questions for me? Yes. Well, I want to at least see the series you compared it to, and I want to see that you figured out that you determined like the science, right? Like some cases it's pretty clear. Like I talked through this, but if you just wrote that, oh, it's greater than you, so. But I would I would think for most of us that you might have to like kind of write a little bit just to make sure it makes sense. So this is really all I'm looking for here. If you can do this much, then great. And that's it. Like it's not anything crazy. Now you might want to say this one diverges my P series, right? Because you don't want to just have, oh, this series, I'm just going to say it converges in there. You want to say this one's divergent by P series, right? So then I know this one's divergent by comparison. Here, I'll add what might be what would be good enough. That's good. Right, and that was greater than, so it's okay, does that make sense? Just if you use the series, know why it's divergent, right? Tell me why you know it's divergent. Don't just say, well, I just look up the numbers, and so I think this one's convergent. So I'm just gonna say this. Okay. Let's go to another one. We're gonna have the sum from n equals 1 to infinity of, let's see, do I want to just do the next one? Or Okay. I'm gonna jump to number 10 in the book. Which is gonna be, so we're gonna have the sum from n equals 1 to infinity of k, sine squared k over 1 plus k. Okay. So, it's gonna take a little bit more effort from us, right? Let's think about this first, right? Sine squared k. Can that be any value I want it to be? No, it can't, right? Sine only goes between -1 and 1, so sine squared only goes between 0 and 1, right? Because you just square all the numbers in there, right? So, at any time, right, sine squared is always less than or equal to what? What number? 1. Okay, does that make sense, everybody? Again, it's bounded, right? It's sine's bounded between -1 and 1, so sine squared is bounded between 0 and 1. So I'll just use 1, right? Because that's the biggest it can be, right? Now, if that's 1, right? If I say that's less than or equal to 1, right? Then every term, then what I can do is I can compare this first to a series where I just say, okay, well, sine squared k is less than or equal to 1. So this whole thing is going to be less than or equal to k times 1 over 1 plus k cubed. Okay? And again, we can do this because all these terms are positive. So if it's, I'm getting just the maximum out of each value. I'm not only getting like a portion of them between 0 and 1, I'm getting the whole thing each time. Okay? So this is less than or equal to this. Okay? So again, -1 is less than or equal to sine, less than or equal to 1. So sine squared plus 1. Square both sides. No, it can be 0. Good. So we have this, right? Now, do I know the convergence or divergence of this one? All right off the bat. What is it? It's not divergent. This is actually going to be convergent, right? We can't look at this directly in Cal, so we're going to need to compare it, right? Now, let me ask a question. If I take out the 1, and I just have k over k cubed, is this going to be bigger or smaller than this guy? Bigger, right? Because that 1 makes the denominator bigger, which makes the whole thing smaller. So, I can create another inequality here. Okay? Now, I have k over k cubed. That's just the same thing as 1 over k squared. Okay. Now, does 1 over k squared converge? Yes, it does. By what? By how? So that's convergent by p-series, right? So what that means is that this one is convergent by the comparison test, and further, since this one's convergent by the comparison test. So there we go. So you might have to do a couple, right? You could technically do both at once if you just knew that, I could write this as less than or equal to 1, and then take out the 1 here, be fine, but sometimes it's helpful to take steps at a time, because you don't want to say, oh, well, let me just, because I'll do an example here in a bit, where there might be 2 numbers, you might say, oh, take them off, it's less than, but it may not actually be true. So, good to be careful. Any questions for me on that? Before we do one more, at least one more. Okay. Let me see. Let's do trying to see if there's like a good. Okay, we're gonna do number 20 now. Which is gonna present us with an interesting scenario. Okay, because this is like the most simplest version of comparison. There's still another layer that we're gonna get to, which is gonna come through in the problem. So we have the sum from n equals 1 to infinity of n squared plus n plus 1 over n to the 4th plus n squared. Okay. So we first want to start this one off to see if there's like some way that we can simplify this down. Okay. So so let's think about this, right? I don't know. What's ideas? Anybody have any ideas for what we can do here? What is it? The top's not a perfect square, actually, in this case. It would be if it was 2 ends, but in this case, it's 10. Okay. So I might actually advise against factoring, not because you might couldn't necessarily do something with it, but it won't really lead us in the optimal direction, I guess, if we're thinking about doing partial fractions of some sort. That would basically just leave it in the same scenario, I think. So I wouldn't want to multiply by n. So just like in these ones, right, we were wanting to find something that we could take off, right? Something that we could say, well, I know that if I took this thing off, then this is going to be smaller or bigger in this way. Okay. So yeah, so maybe we can start with this one, right? So if I take off this one, am I going to get a series that's bigger or smaller? It's going to be smaller, right? Because n squared plus n plus 1 is bigger than just n squared plus n, right? So we're going to get so this is going to be greater than or equal to, and we're going to have n squared plus n over n to the 4th plus n squared. Okay. Now, yeah, so we could factor an n out here. So if we factor here, right, we get n times n plus 1, and we get n squared times n squared plus 1. Now I could cancel an n. So maybe we can try to do that, right? So there's an n here and an n here. So this is the same thing. This series is equal to n plus 1 over n times n squared plus 1, right? But now we're still at a bit of a standstill. You could try to, again, maybe we could take it and do partial fractions or something, but this is a little, it's probably not going to be very good for putting these together, right? Because if I put my 1 and infinity here, I'm going to get 1 and then 2, and then I get 2 and then 5. Like, they're not going to cancel out extremely well. So maybe that's not the route. So instead of leaving that factored, I'll go ahead and multiply this, so we get n cubed plus n. Okay. I could take off another one, maybe. Okay. So we could do that. So we get n over n cubed plus n, so I can do, right, does this make sense? N plus 1 would be bigger than n, right? So again, I can just take off the number. Okay. That's equal to, so we get 1 over n squared plus 1 in that case. Okay. That's cool. What do I do here? Okay. So remind me, is this one bigger or smaller than one that's squared? Okay. So what's the problem? Yeah, notice we have all these greater, but now we have less. Oh. Okay, so I mean, we could say that this is convergent, right? Because we know this one converges, right? But you have that it's smaller than this one, and that it's smaller than this one for sure, right? Just because I have a convergent series, right? Right, notice the direction of these, right? I said if it's less than and it's convergent, then and this one's convergent, it's convergent, if it's greater than and it's divergent, it's divergent. I cannot say the other way around, right? I can't say, oh well, you know, let me just kind of demonstrate with like public curves, right? Like, oh, I know that this sum here of all these points is going to converge, right? Because it's going down. So since all of these points are greater, that's going to converge too, right? That doesn't make sense. Like I can't use that logic. It only goes one way, right? So what do we do? Okay. Well, first, let me make a suggestion. Let's instead of kind of taking all these steps here to break this down, I'm gonna cut it short by 10 points, okay? I have n squared here, right? Which is the greatest term, right? After a certain point, this n and this one both aren't gonna be doing as much, right? But also these guys, right, are gonna make the terms bigger each time. So I don't need to just take off the number, I could also take off n here. And then down here, I can just leave the n to the 4 because n to the, oh, actually, no. What did I want to say? So I could take off both n and 1 here, right? Now, an immediate issue, the reason why I chose this one is because on this one, right, we didn't have anything happening in the top when we just said, oh, well, it's in, it's minus the bottom, so then it'll be greater, right? And this one you have, well, there's a sign part, but then this is plus, so it's gonna be less in this case instead of greater, right? Now we have both a plus and a plus in both the numerators and the denominator, right? So I have n squared plus n plus 1, which if I compared it, right, just taking off these points, I'd say is less than or equal to. But if I took off the plus down here, it would make the denominator smaller, so it would make the whole thing bigger, right? So I kind of have to contrast the signs anyway. So what you would want to do in this case is, right, again, you're going to see several ways that my normal comparison. If you can do an easy one, great. If not, I need to do more careful. So I'm going to take off the n plus 1, I'm going to take off this n squared, leave me with n. Okay? Which then I can just write this as 1 over n squared. Okay? Now, again, there's a weird connection between them because there's not just a straight one direction or straight the other direction. Even if there is a straight one direction, this one's convergent, right? We don't know if this is greater than or equal to. If it's greater than, it doesn't work. So what do? Well, we appeal to something called the limit comparison test, which says we'll call it elements. Okay, and this tells us that we have, so we're going to suppose and so these two series, which I'll write with whatever is on A and B in, both have positive terms. Okay. If the limit as n approaches infinity of, and I think it doesn't matter, and over b of x equals c, where c is a finite number, and c is greater than 0, so it has to be finite, right? So it can't be infinity, but it also has to be greater than 0. It can't be equal to 0 either. Okay? Where c is finite and c is greater than 0, then either both series converge or both diverge. Okay. So let me talk about this in words, right? Limit comparison test. What this says is that if I have two series, if I take the limits of the a_n term over the b_n term, and it's equal to a number c that isn't infinity and isn't 0, but it's some other number in between, then either both series converge or both series diverge. Okay? That means that if there's a constant between them, that means that they're close enough, they're basically just a constant off of each other, so that if this one converges, then this one also has to converge. If this one diverges, this one also has to diverge. Okay? By a simple fact of, oh, yeah, they're related somehow. If I just took this sum, basically multiplied it by this number, I get this, right? So, that's kind of all there is to it there. There's a little proof in there. It just kind of says, it kind of takes this idea of taking the two sums and just saying, oh, well, if it's in some nice number range here and it's bounded, then that means that if this guy converges or diverges, then that a_n one also, by restriction, kind of has to do the same thing. So, limit comparison test. So we're going to use that here to evaluate this one. So we'll demonstrate it. Questions for me real quick, fast for hopping doing that. Okay. Again, does it make sense? Did it make sense through our work here why I couldn't just use these two rules on it? It didn't ask me, clarifying, but doesn't make sense. Okay. Again, this one only works one direction, right? So you have to have a less than, and then b_n has to converge. And then this one only works one direction in that it has to be greater than, it has to be divergent for b_n. Okay? Otherwise, you can't do the other direction, right? Or if you just can't tell a direction at all, like I can't tell here. You know, it's very hard to tell because you have things adding, which makes the numerator greater, but then you also have things adding, which makes the denominator greater. So both the numerator and the denominator get bigger. You can't really, one makes it bigger, one makes it smaller. It's hard to tell which way it goes. So. Okay. Is it okay if would you want me to leave this up and I can just kind of erase this part here, or I don't mind the way. I'll probably just erase that for the moment. Okay. Anyway, so let me kind of recap just one more time. I could, if I have like polynomials, right, then for both the top and the bottom, I can just kind of take off whatever other terms don't have the same power, right? So like n squared plus n plus 1, just kind of throw off that n plus 1. Okay, now, you have the freedom to do that really anytime you're doing limit comparison. If you're going to try to make that work, I wouldn't just throw off everything willy-nilly, because you want to make sure what makes sense, but you know, we want to try to get to the simplest idea. So I'm just like, let's take off all those smaller terms, take off the smaller terms here, so I get n squared over n plus 4. So n squared over n plus 4 is 1 over n squared. Okay, so we're going to compare n squared plus n plus 1 over n to the 4th plus n squared versus 1 over n squared. Okay, so to do this, I'm going to use the limit comparison test. The limit comparison test says to take a_n, which is n squared plus n plus 1 over n to the 4th plus n squared, and divide it by b_n, which is going to be 1 over n squared. Okay, what can I do with that 1 over n squared? And the denominator? What is it?
You can flip it and then it ends up canceling out the n squared on the bottom.
Oh, it cancels out an n squared on the bottom, you're saying?
Yeah.
So we get n goes to infinity, so I'll write it real fast, so we have one, and then n to the fourth plus n squared times, yeah, we're gonna get n squared over one, so yeah, we can either just multiply this straight across, or you can say, okay, well, there's n squared down here, so it'll cancel. Maybe I'll do that for our case, so we're gonna get the limit, and then approaches infinity of n squared plus n plus one over n squared plus one. Can I do the limit of this thing?
Yes.
Yes, what is it?
Then it's only going to be one.
One. Okay, good. Is that a number between 0 and infinity? Absolutely. So that means that if b of n converges, then a of n converges, and if b of n diverges, then a of n diverges. Right? So what does b of n do? What does 1 over n squared do? Does it converge or diverge? Converges. Good. So this one converges. So what can we say about our original series? Converges by, I'll just write it out so you can compare it. Okay. And this one converges by B series, right? We go by. Okay, question for me, yes.
So, how did you, how did you know the signs of that 1 over n squared for the limit comparison? Like, did you try to, like, how did you know to get that?
Yeah, so the idea there was to, like, when it comes to polynomials, the easiest thing if you want to try to find a series to compare to is just to take off all of these extra terms that don't contribute to the leading one, right? So I took off the n plus one, the n squared here. In truth, you have a lot of options. You don't have to be restricted to this. However, if you make a bad choice, which maybe that's what I should talk about, if you make a bad choice, the limit comparison test is going to show it. Because, you know, because I mean, let's think about a silly example, right? Obviously, this is positive, right? And all the terms here are going to be positive, right? So this series is greater than or equal to sum from n equals 1 to infinity of 0, right? That's a comparison, right? So let me take the limit of that, right? But if you do, you would have 0 in the denominator first, right? Which would just make it go for infinity. So you're like, oh, well, that didn't help me, right? That doesn't say anything, right? So there's a bit of freedom. There's always one that's going to be the most obvious, just by like taking off the littler terms, the terms that don't do as much. But
So, would you look to off the term and like the highest power?
yes, keep the highest power. Mhm. Yeah, if you don't see something like this you can do directly and compare and see it, then just take off everything to the highest power and do that. Okay, or you know, again, it's not kind of depends on what you go with, but if polynomials take off, you know, whatever the highest power is, or yeah, again, it's kind of a case by case. If you run into the problem like something that you're unsure about, I can answer as well. But good questions for me on that. I might do one more real quick. Great, yes. Oh, like if you have like sine or cosine, I understand you're saying that. So usually, yeah, and in the case of now for our sake, at the moment, the only thing we're really going to be dealing with is like the sine squared, because we don't really want to bring normal sine and cosine, because we're only dealing with terms that just have positive numbers at the moment, or mostly like these basic ones. So maybe we'll talk about that more in the next section. The only reason we take out the sine squared is because, oh, well, it's positive, so it's be less than. So if you have the whole thing, a little more sketchy. So just be worried. Especially with the limit comparison, it doesn't have positive terms always, so. Anything else? Any other questions for me? Okay, let's do another one. Let's read the watch. Let's see, so we have a series. Last series we'll do for now. We're looking great. It is. We have a sum. N equals 1 goes to infinity of n plus 3 to the n over n plus 2 to the n. Okay. Again, you can try to use the basic rules, right? Just try to find the easy. Just take off this piece or take off this piece. What we're going to find is that since it's adding both in the numerator and the denominator, we kind of run into issues because both the numerator is, if you take off the n, right, you get a number that's smaller, but if you take off the n down here, you get a number that's whole number that's bigger, and so they kind of cancel each other out. So this might be a good chance for a little comparison. Now, you could always use a little comparison. Sometimes it'd be quicker to not, right? You don't have to do it every time. If you can find easy comparison, just do it. So let's find something to compare this to. So in this case, it's a little different, right? We were just talking about polynomials taking off the terms of lowest degree, right? Now we have 3 to the n and 2 to the n here as well, though, right? So let's think about this. Which is going to grow faster, n or a number to the n? A number to the n is going to grow faster. Okay, so whichever one's going to grow faster is the one that you're going to want to keep around. So in this case, I'm going to take off the n's and I'm going to be left with 3 to the n over 2 to the n. So there's another example, like maybe to consider about, like just what grows faster. In this case, the 3 to the n and 2 to the n. Okay. Do we know what type of series this is? It's a geometric series, okay? Yeah, so this is the same thing as n equals 1 to infinity of, and I can write 3 over 2 to the n. Do we see that? I can just, they're both to the n power, so just pull to the side. Is that a convergent or divergent? It's divergent. Okay. So what we want to show is there, can I, if I divide them and take the limit, you know, does it, do I get a number out of it? Okay. So we're going to take the limit as n approaches infinity of an, which this is my an term in this case, and this is my bn. So we're going to take n plus 3 to the n over n plus 2 to the n over big over 3 to the n over 2 to the n. Okay, this can flip, and we're going to multiply it, so I'm going to get the limit as n approaches infinity of n plus 3 to the n over n plus 2 to the n times 2 to the n over the n. Yes.
So, alright, I have a lot of questions. At that point where you said, where you wrote 3 over 2 to the n, and like you knew that was divergent, right?
Mhm.
Should you stop there and just do the comparison?
No, not in this case because we don't know if this is greater or smaller,
Okay, gotcha.
right? Because it's adding them both.
Mhm.
You're adding in, which makes it bigger, but you're also adding in the denominator, which makes it smaller. So you can't really tell. In that case. So we have to go ahead. Okay. Let's see. Now let's think about how we're going to finish this one off. Okay, there's a few ways we can go about doing this. Maybe the idea would be, I'm going to take, maybe let's just go ahead and multiply it across. So I'm going to get 2 to the n times n, plus three to the n over third times two to the n over three to the n times n. Plus two to the n times three. Okay. Now, could we use L'Hopital's rule on this? Yes. Would you want to use L'Hopital's rule on this? Probably not. So the easiest way, I would say to think about this limit is this, and that's going to be, let's see, trying to go. Notice that this part, this piece, and this piece are the you guys figured it out as well. We are. Let's see. I'm gonna try another example. It's gonna be n plus. This is what I want. Okay, here we go. Let's do this instead. I'm gonna take, what I'm gonna do to demonstrate this limit, I won't use this one like that. That's what, I'm gonna take the thing with the three to the end and put them together. So I'm gonna get n plus three to the n over three to the n. And then I'm gonna do two to the n over n plus two to the n. Okay, now why am I doing that? Well, remember that if I'm taking a limit, and as long as both limits exist, then I can take the limit of each piece. So I'm gonna assume that the limit does exist, and I'm gonna take the limit of each piece. So I'm gonna take the limit as n approaches infinity of, now for this guy, I can take 3 to the n and divide it. So I'm gonna get n over 3 to the n plus 1, right, with 3 to the over 3 to the n. And then times the limit as n approaches infinity of 2 to the n over n. I can't really do that. Okay. What is the limit as n approaches infinity of n over 3 to the n? What do we think? N over 3 to the n. What is it? 0, right? Yeah, you could do that. I mean, you can just think about it and say this grows faster than this guy, or we could use L'Hopital's rule where you have 1 over 3 to the n times 10 to the power 3, which is derivative. But this is going to end up being, that's going to end up being 0, so I get 0 plus 1, which is just 1. Okay? Here, I get, again, I could use L'Hopital's rule here, or we could just think about it, right? I have 2 to the n over n plus 2 to the n. After a long time, that n really isn't going to affect much, right? So what's going to happen is the behavior is more just like 2 to the n over 2. Another way to look at this is to say, like this part in particular, is to say the limit as n approaches infinity. If I divide 2 to the n to the top bottom, I get 1 over n over 2 to the n. Plus 1, which again, this limit would be 0, and so I get 1 here. So we get 1 times 1, which is just 1. So they do converge. Like they both exist. Okay, that's between 0 and 1, 0 and infinity, right? So what does it say about this series? They converge or diverge? It diverges, good, since the limit was semi beside 0 and k. So that shows it's a good pick. Might not be the easiest pick to work with, but it is a good one. What is the optimal? Still the optimal one, right? But any other choice you try to make would be a little bit. We get the answer to this one is. So this is divergent by geometric series, and being a geometric series, so that's divergent by whatever. Okay. Questions for me? Again, I won't give you a limit that much, so like obviously it'd be nice if you, play around with the picture and understand it, but I'm not gonna require it of you in my question scenario. So questions at all for you? No, you're fine. Not infinite sum. The limit goes to 1, right? That doesn't mean, I'm not saying the limit of the series goes to 1, right? This limit here is the limit of a over b, right? We said if c is finite, c is greater than 0, if that's our 1, then either both series converge or both diverge. So we got 1, right? And so that means C is good. That means both either converge or diverge. Well, since 3 over 2 to the end diverges, that means this. Okay, so this limit doesn't directly relate to the sum. It relates to how the two terms are related. Okay, we good? Questions for me at all? Anything else before we take a break real fast? Suppose not. Okay. Then, say like 505. I'll probably end up talking a little until then. So, just for other questions. So, 505 will be we'll say it's the third time.